to my browser here, I've got a Google spreadsheet open wherein I'm storing the title of one of my favorite TV shows, The Office, and then I have a lot of TV stars who featured in that show, Steve Carell, Rainn Wilson, and so forth. But even in the world of spreadsheets, I would argue that this way of associating TV stars with the TV shows they were in is maybe not the best design. Why? Well, here I have just 5 of the TV stars from The Office, but there were certainly many others in that ensemble show. But so where does this design end? Do I add another star column, another star column, another star column, and the like? But that doesn't seem like the best design, because then when I add a second TV show to this same design, then I'm going to have a different number of stars for that show and a different number of stars for the next show and so forth. So this doesn't feel like the best design to use columns to store each and every TV star in a TV show. Well, let me propose that we look at a second version of this that I whipped up in advance, whereby maybe we stick to just 2 columns. I like this better because from the get-go I've got 2 and only 2 columns, and this thing isn't going to grow wider and wider with more and more TV stars. But I also don't think I love this design. Why? Well, because in the first column I've got the title of the show, The Office, but I've got it again and again and again and again, one such row for every TV star in the second column here. So this feels more compact, sure, but there's a lot of duplication now. I'm literally repeating The Office again and again and again. So the right way to do this, not necessarily in the world of spreadsheets, but as we'll soon see, in the world of relational databases, is as follows. In fact, it's just convenient visually for us to use a spreadsheet just temporarily to mock up this idea. But I dare say the right way to solve this, as we'll soon see in relational databases, is not even with a single sheet, but rather to start using our database tables, or in this case, temporarily sheets, to represent real-world entities or relationships therein. In particular, notice at the bottom of my Google Sheet here, I have a Shows tab, a People tab, and a Stars tab. In other words, in the world of TV shows, there are, of course, the shows themselves. That's a real-world entity, each and every show. But there's also lots of people in that industry, the actors, the writers, the directors, and so forth. So people is another real-world entity. But then there are the people specifically who star in those shows. And that's more of a relationship. So we've got entity, entity, and relationship. So notice here in my Shows tab, I have the beginnings of a sheet for just all of the TV shows in the world. There we have in the second column, The Office, which is the one we keep talking about. And just for the sake of discussion, let me propose that it will be advantageous to us and good design to assign every TV show in the world a unique ID. Doesn't really matter what it is, but some unique number that no other TV show is using is probably helpful. So for The Office, for instance, I'm going to arbitrarily, but deliberately, we'll soon see, use 386676 as its unique ID. Meanwhile, if I click on the People tab now, here are the real-world people. That is to say, people are an entity unto themselves. And here we have, again, Steve Carell, Rainn Wilson, and so forth, each of whom has their own unique ID, which is, again, an integer. And it could be the same numbers as before, but in the context of people, these IDs must be unique. In the context of shows, these IDs must be unique. So there isn't necessarily a relationship yet. But if I go to the third and final sheet here, the Stars sheet, notice somewhat cryptically, I have no TV shows, I have no people, but I do have the unique identifiers for both. And the way I propose to maintain relationships between shows and people is by somehow linking their unique identifiers together. So if I want to associate Steve Carell and Rainn Wilson and other people with The Office, I include their ID, and so forth. But in the left-hand column, I associate those person IDs, so to speak, with the corresponding show ID. Now, I do concede that there's still some duplication here. I keep seeing 386676. 386676, which is obviously the ID for The Office. So there's still some duplication here, but the duplication does not extend to these longer strings of text, The Office, but rather these smaller integers. And that I'm going to be okay with. In the world of relational databases, we shall see it's very common and generally good design to use simple integers, but but unique as your identifiers for data. It's okay if you have duplication, therefore, of those integers, because what? It's 32 bits, maybe 64 bits. It's not a variable number of characters, as would be the name of a TV show like The Office, or heck, a TV show with an even longer name. We can gain efficiency by just using simple integers. But unfortunately, this spreadsheet, I do concede, is no longer nearly as useful to look at as the previous versions, because if I want to see shows, I have to go here. If I want to see people, I have to go here. If I want to figure out who stars in what show, I have to go here. But these numbers mean nothing to me, the human. But that's why we're transitioning now away from these spreadsheets again to a proper relational database. Because with SQL, this programming language, we can somehow join these disparate data sets together and get back the answers to the questions we want to visualize exactly the data we want, but underneath the hood, so to speak, all of the good design will be intact using integers to relate one piece of data to another. So indeed, in the world of IMDb, we're about to see even more data than this. In fact, what we'll see now is this so-called schema. And recall from earlier that the schema for a database is the design of that database. And it turns out there's fairly standard ways of drawing databases and database tables therein and the relationships between those tables. But we'll focus step by step on subsets of this data here. But the picture you see on the screen here really represents a shows.db database containing lots of information on TV shows from IMDb that's apparently going to have 6 tables. And among those tables, at top left, are the people table. And then we have, at bottom left, the stars table. In the middle, we have the shows table. Below that, we have a writers table. And then above that, in top right, we have the genres table, which will give a genre to each of these shows, and the ratings for each of those shows. And indeed, that's among the reasons IMDb is popular, is that it offers up ratings or people's evaluations of these various films. But let's indeed focus on just a subset of this for a moment. Let's focus on the world of TV shows at left, and at right, the ratings thereof. Now, technically, these two tables could be combined into one, but insofar as ratings are such a prime feature of IMDb, and they themselves are sort of a real-world entity, the ratings for shows, IMDb chose to store ratings in a separate table, or technically TSV file, so we've opted to do the same for consistency with the original data set. But let me go ahead now and open up VS Code again, whereby I still have my files from earlier, but we're done with those, favorites.csv, favorites.py, and favorites.db. But during break, I also copied into my code space a big database called shows.db, which is like 50 megabytes of data from IMDb itself, as seen in top left of my Explorer. Let me go ahead and close the File Explorer, though, for now. Let me increase the size of my terminal window as before, and let's go ahead and open up this new shows.db file. I'm again going to use SQLite 3. Shows.db, enter, and rather than create this file, which I did the very first time with favorites.db, this one I showed you already exists, so I'm simply opening it by running SQLite and then the file name. Let's just go ahead and start wrapping our mind around some of this data. Let me go ahead and do something like select star from shows semicolon. Again, my sort of go-to default command, just when I want to get a sense of what is it I have in front of me. Enter. And it's taking a while now. All of our favorites thus far kind of flew across the screen, but we are looking at decades worth of TV shows now flying across the screen here. So I would wager that we've got not even hundreds, but thousands, tens of thousands, hundreds of thousands of TV shows. This is a very large database. And so we're now going to really be applying the principles of good design to make sure that when we execute queries, when we design databases, we're indeed doing it well. Because you can imagine for real-world websites like IMDb, you can't really afford to make poor design decisions because real-world users are using that site. They want to get quick results. You want to minimize the number of servers you have, the amount of money you're spending. So good design decisions aren't going to just translate into good problem set scores now, but actual time and cost savings in the real world. In fact, that was a lot of rows flying across the screen. Let me clear my terminal for a second, and let me just do a quick select count of star from shows semicolon, and indeed we'll see there's 234,000 TV shows in the database as we have saved it here. If I want to see just the first 10 of those shows, there's other syntax I can write too. Let me go up in my history, and if I don't want to see 240,000 rows all at once, well, I can limit myself to the first show, or maybe more usefully, the first 10, just so it fits on the screen. And indeed, we have a bunch of shows from the 1970s, one from 1981, and if I limited it to even more rows, we'd see more and more films. But what is it I'm looking at? Well, it looks like in the shows table, I indeed have an ID for the show. I have a title for the show. I also seem to have the year in which the show debuted on TV for the first time. And as of now, the total number of episodes that are associated with that show. So it's a helpful way to just look at a subset of the data just to see what kinds of data is there, even though it's non-exhaustive. How about the ratings? Let me go ahead and do the same thing. Select star from ratings limit 10. Whereby I just want to wrap my mind around this table as well. OK, I can infer here that in one column is the show ID, which I'm guessing corresponds to the ID in the shows table that we just looked at. There's a rating column, which seems to be out of 10, I'm guessing, from 0.0 to 10.0 for an average. And then the number of votes by real-world humans on the internet that contributed to that average rating. So just at a glance, I can kind of infer what this data set looks like in the absence of any additional detail. Now, what you'll see here implicitly is an example of what we would call a one-to-one relationship. It turns out that with relational databases, you can indeed have these relationships across tables, and they can be different types of relationships. One-to-one means that every show has one rating, according to the design of IMDb's database. And I can kind of infer that as follows. If I have in my shows table up here an ID column that I'm inferring, and I could confirm from IMDb's documentation, uniquely identifies each of these shows. When I then see in another table a column that by convention is called show ID, the implication is that that's not a unique identifier for this table's rows, but it's a reference to, if you will, another table's unique IDs. So this is just one convention, and there's many in the real world, but in the original table where the data is defined, like TV shows, the unique identifier is typically called ID. But when that same identifier is used elsewhere in another table for cross-referencing purposes, it is typically written as table name underscore ID, but you change the pluralization to be singular, so show ID means that it probably comes from a table called shows in the ID column. So I'm just inferring, but frankly, again, per the documentation, I bet I could confirm as much. And if indeed we do go back to the visualization of this database and take me away, you'll see that the arrows drawn between shows and ratings actually implies this kind of relationship, whereby every show has a one-to-one relationship with its one rating in the other table. Now, how can we go about wrapping our minds a little more formally about what's in this here database? Well, let me clear my screen, and let me use that schema command, but let me use it slightly differently. Previously, for my favorites.db, it just showed me the schema for the design of my favorites database. That was super simple because that was all automatically generated from that .import command. This database, again, I claim we created ourselves using IMDb's own data. So what we did in advance of today is this. If I want to look at the schema or the design specifically of my shows table, it looks like this. And we've tried to format this line by line to be a little more readable than the automatically generated one for favorites. So at some point, we, the staff, ran a command called create table, and we created a table called shows. Inside of parentheses, we then specified what are the columns for that table. The first one we decided to name ID. And we decreed that it's actually going to be an integer, a number from, say, 1 on up. The next column is going to be a title column. It's going to be text because, of course, The Office and other such TV shows have text as their name. And in particular, we want to make sure that no TV show's title is null. After all, if it's null, that means we don't have it. Why is it in our database? So that's just kind of a business decision. I do not want blank data, null data, in my database because what would it even mean for a TV show to have no name? That's not really useful data at all. Then we have a year field, which, yes, is an integer, but it turns out for things like years, it turns out that it's SQLite. You can specify more generally that it's a numeric value. So it's like a number, but it's a special type of number, like a year. It's not just a boring old integer. Episodes, though, is just going to be an integer because we just want to count 0, 1, 2 on up. There's nothing really special about that. And then the last thing here, after the final comma, is a little different, but we'll come back to this, whereby the primary key for this table is ID. And for now, that just means that the unique identifier for this here table is going to be the aforementioned ID column. We're just telling the database what to expect. Meanwhile, if I do .schema ratings, which is that second table, very similar in spirit, but notice this. I've created a table in advance called ratings, and inside those parentheses there are these columns. A show ID column, which, like the ID column earlier, is indeed an integer, but be careful here, it is not null. It would also make no sense if we've got this orphaned rating that has no relationship to a show, so we do not want show ID to ever be null. That rating has, of course, a real number as its value. So a real is similar to a float in C or in Python, whereby it has a decimal point, and that's apt for something like an average. And it, too, is not just real, but also not null. And then the number of votes that contributed to that average is an integer, because there's some number of humans who voted. That, too, should not be null. But the interesting part here, and here is the relation in relational database, notice that this last line of code here specifies when creating the ratings table that there's a relationship between this table and another. Specifically, show ID in this table somehow references the ID column in the shows table. And you'll notice sort of some keywords here. Primary key is what I said defines the uniqueness of the column. Foreign key is what imposes the relationship between this table and that. So henceforth, what we mean by primary key is a unique identifier for a table's rows. It is guaranteed to be unique row by row by row. A foreign key, meanwhile, is just the appearance of a primary key in some other table for the purpose of relating that other table to the original table. So it's foreign in the sense that it's the same number, but it's in a foreign land. It's in a different table that's somehow referring back to the original table. So this is just jargon, but at the end of the day, what's kind of nice here, these are just numbers. And we've tossed on a bunch of terminology here and jargon, but really we're just talking about reusing numbers so that we know, just like my visualization with the Google spreadsheet earlier, that there's a connection somehow between these two.